All right, so for power, this is actually going to be a fairly quick set of notes. It's not going to be too bad here. Power is simply the rate of doing work. So we've talked about energy, we've talked about work, we're now talking about power. Often people interchange these three things, but they're distinct items. So power is the rate of doing work, just like speed is the rate of changing distance. So all that means is if it's the rate of something, it means how much time does it take to do something. I basically already said that. So when we talk about doing work, we don't care about time. So if you want to get all technical with some of your teachers and asked if you did your work during class time, it doesn't really care about the time, so you can say, yes, I've done it, even though you're going to do it later, because it doesn't matter about time. As long as you get it done, it's done. Whereas power depends on time. And it's measured in two things. You can either do joules per second, or you could do watts. So you've probably, where have you heard the term watts before? Electricity. With your light bulbs. When you're buying a light bulb, you've got a 40-watt light bulb or a 6-watt light bulb. So that all depends on how much work is done in a given amount of time. Is that the end? Yeah. So here is your equation. Power is work over time. And because we know work is also change in energy over time, work is also change in energy, I can exchange it with this. Technically, you could also do it as force times distance over time. But these are the main ones that you will see. Any questions with this? Anyone feel like their brain is hazy from having a week off? I definitely do. Is there anyone still writing this out? Okay. So examples. So Lover's Leap, this is an actual place, I think. I've never been there. It's 122 meters vertical climb. So the record time to get up this is 4 minutes and 25 seconds. What is the average power output? So this is a common type of question. So when you're looking at your equation, we have two parts. We got power equals work over time or change in energy over time. Which of these two things am I going to use? Am I going to use work over time or am I going to use change in energy over time? Work over time? Is the work given?
Yes.
We don't have work, but I have time. But notice both of these have time. So in this one, because we're not specifically told work, or we're not told it's from this amount of joules to this amount of joules, we want to deal with change in energy. Because what kind of energy is changing in this question? It's either potential or it's kinetic. Okay, let's think about this. So kinetic energy has to do with what? Movement, right? So kinetic energy has to do with movement, and it has to specifically do with speed, right? Kinetic energy is a half mv squared. Could we figure out a velocity with this? We could, right? I've got a distance, I've got a time, but does his velocity change? I don't know. Maybe. We don't know what his velocity is. It doesn't tell us anything about that. So let's look at potential energy. What does potential energy depend on? Gravity, and it depends on your height. Right? So does his height change in this question?
No.
He's climbing up a mountain or a hill or something, cliff. So yes, we are dealing with a change in energy. And specifically in this case, we're dealing with potential energy. So that's the trick with figuring out which type of energy changes. Moving up or down, most likely potential. Moving side to side, but a change in velocity, kinetic. So if there's a change in speed, deal with kinetic. If there's a change in height, deal with potential. If there's a change in both, you'll have to deal with the change in both types of energy. But typically we just deal with one type. So this is the one that I want to use, because this I can figure out. So power is going to equal a change in potential energy. So in this case, we'll have mgHf, so final potential energy, minus mghi, his initial potential energy, all over time. So I just skipped the step saying potential energy final minus potential energy initial, and just wrote it out like this. Anyone stuck at this point? No, this is not with the conservation of energy. This is just continuing with potential and kinetic energy. So you don't need conservation of energy to be able to do this. That's a great question. So let's think about this. So here's our cliff. Here's our person. They start at the bottom, and eventually they reach the top. So we're told that this height, 122 meters, this is what's happening initially. Here's our final position up here. So remember, with potential energy, I can set my 0 point wherever I want. Right? I could set it at ground level, I could set it at the top technically, and start off with a negative energy. I could set it somewhere underground. But if I set this as my energy does not 4. If I say that this is where EP equals 0, what's my initial potential energy? 0. Because my heights are all relative to this point, the ground. So conveniently, this turns to 0. So I don't care about that. And then I'm just left with mgHf over time. I have mass. I have G, 9.8. I have the height. And I have time. So we're good. We can solve this. Mass, we're good. 65. G, 9.8. H, 122. Time, we've got 4 minutes and 25 seconds. Do I put that as 4.25? No. I need this time to be in seconds. So in order to turn this into seconds, what do? Yeah. So 4 times 60 will give me how many minutes, or sorry, how many seconds in 4 minutes? Plus 25. Because I want it in seconds. Plug all that in. 290. Again, the unit is watts. Power is watts. Thanks, Adam. No, Jen is in the worst spot, sitting right behind the computer screen. Any questions on this? Or are we good? So you'd use W over T if I tell you specifically the work number, or you can get work really easily. So it all depends on what you're given in the question. So just like the big 3 equations, you pick it based on what's in the question. Any other questions? Okay. So you've got the certain note? You got, okay. I think this is the last one. No, we're getting there. Okay. So let's try this one. We've got a car accelerating from rest to some velocity. Right off the bat, as soon as you see rest to some velocity, we know immediately we're dealing with kinetic energy, because you were already told the velocity changes. So we want the power output of the car. So what's the power? Ignore friction. This is useful in this case. So again, I'm just going to assume we're going to use this equation. We're not told anything about work, so let's just ignore that and jump straight to change in kinetic energy. So if I do this, let's write out the steps this time. So change in kinetic energy is just the final minus the initial. If I'm starting from rest, what does that tell me? Yeah, initial energy is 0. If I'm starting from rest, my velocity is 0. If my velocity is 0, this is 0. So conveniently that cancels out. We can actually calculate this. So again, using the equation from kinetic energy, we've got a half mvf squared. If you don't have this memorized by now, don't worry, it's on the formula sheets. And do I have everything I need for this? Do I have the mass? Yes. Yeah. Do I have the final velocity? Yeah. Yeah. Do I have the time? Yes. All right, I'm good. Can you see how kinematics could sneak back into this? How could kinematics jump back into this? Yeah, so I could give you acceleration instead of the final velocity. I could give you distance and time and the initial velocity. You'd still need to figure out something. So if you thought kinematics was long gone, you should know by now. I'm sure if I went back and gave you the kinematics test now, you'd think it would be really easy. These numbers are rounded, so if you get a number, it'll be slightly off from this, but this is a rounded number. Any questions on this? Mm-hmm. This part, where this came from? So this is the equation for EKF. So just in general, your equation for EK is a half mv squared. Yes, yeah, this is on the formula sheet. You will not see on the formula sheet power equals change in kinetic energy over time. You'll just see power equals change in energy over time. So you'll need to figure out when it's kinetic, when it's potential. Any other questions?
Where we have examples where like EKI is 0?
Yes. So I could give you this, and instead of saying from rest, I could say from 5 meters per second to 15. So then all you would do for this, instead of canceling it out, it'd be a half mvf squared minus a half mvi squared. And then plug in the numbers and solve it. Yeah, so that's entirely possible. Same thing with the potential energy. I could give you one where the initial is not 0. We're almost done here. So this is another part that we could consider with power. So we'd have power equals work over time. Work is also equal to force times distance. Let me show you the next step here. So since velocity is equal to d over t, I can do a substitution here. So I've got d over t, and here I've got d over t. Because of this, I can make an equation that looks like this. So this should seem like it's a pretty easy equation to use. However, there is something special about this equation. So if you think way back into kinematics, and you think about this equation, what's special about this equation? V equals d over t. Other than that, it's really simple. Technically, yes, this is speed instead of velocity. I could change this into a velocity equation by just doing this and saying it's vectors. But I don't always put those vectors. Exactly. So this equation only works if I have a constant velocity. If I have some sort of acceleration, this equation doesn't work anymore. So this equation's nice, and it's great, and it makes your life a lot simpler. However, it only works if you have a constant velocity or constant speed. Constant velocity slash speed. So in your notes somewhere in there, make sure you highlight this, put a few stars by it. This equation only works with constant velocity. So this is going to be given on your formula sheet. It's there, but it does not say constant velocity. So you will need to know that this equation is only useful when you're given constant velocity. Otherwise, you'll get a wrong answer. Essentially, this is just saying V average. So this is why it's really useful. So we've got a student pushing a block at a constant velocity. What's their power? Really easy. Power equals force times velocity. We have the force, we have velocity. Really, really straightforward. Gives you 310. Questions with that? Has anyone started to realize that the questions I give you in the notes are really easy compared to the practice problems? Yeah. What's that? And compared to the test, yes. If you saw this on the test, you would love me forever. I do have simple questions like this on the test, yeah. The only thing is this, I can't give you many marks for this. I can only give you 2 marks, whereas multi-step I give you a lot more. Yeah. Is there one more thing on there? Pardon me? Something like this does show up on unit test, yeah. You haven't done this unit test yet. See, so Adam, with this we could talk all about the philosophy of test writing, and we can get into like the psychology of it, and if I gave you a test that's only these easy questions, am I really testing your knowledge or not? Or then you get the test where it's like, okay, pick 5 questions to do, and there's a range from easy, medium, and hard. And if you do just easy ones, you get a 50%, and if you do just hard ones, you could get 100%. I'm just saying we can talk about test philosophy when we talk about if we just do the easy questions.